Hey everyone, so today we're going to dive into electrochemistry. It's this incredible, invisible force that's pretty much running the modern world. We're talking about the science of how chemical energy and electrical energy can swap places, and it connects some things you would never ever expect. I mean, seriously, think about it. What in the world could a high-tech smartphone battery possibly have in common with a creaky old shipwreck slowly falling apart at the bottom of the ocean? They seem like they're from two different universes, right? But believe it or not, they are driven by the exact same core scientific principles. And it all boils down to this: the flow of electrons. That's the secret sauce. Whether we're carefully controlling that flow to power your phone or it's happening all on its own, causing a massive ship to corrode, it is all electrochemistry in action. Okay, so if we want to get a handle on this flow, we first have to really understand the chemical reaction that makes the whole thing possible. This right here, this is the heart and soul of electrochemistry. And that reaction is called a redox reaction. It's short for reduction-oxidation. You can think of it like a dance where electrons are passed from one partner to another. The substance that loses electrons is said to be oxidized, and the one that gains those electrons is reduced. The key thing to remember is that you can't have one without the other. They always happen together. Now, here's where the language gets a little bit tricky, but it's super important. The substance that gives away its electrons, the one getting oxidized, is called the reducing agent. Why? Because it causes the other substance to be reduced. And on the flip side, the substance that grabs those electrons is the oxidizing agent. It's all about what you're doing to your partner in the reaction. Keeping track of where all these electrons are going can get complicated fast. And that's where the half-reaction method comes in to save the day. It's this really systematic, step-by-step way to balance these equations. You literally split the reaction into its two halves, the oxidation part and the reduction part. Then you balance all the atoms and charges, adding things like water, protons, and of course, electrons. Once both sides are balanced, you make sure the electrons are equal and you smash them back together. It's like chemical bookkeeping, and it makes sure nothing gets lost. So, we've established that electrons are on the move. The next big question is, how do we actually turn that movement into something useful? Like electricity. Because if you just throw the two reactants into a beaker together, sure, the electrons will transfer, but all that amazing energy just gets wasted as heat. So how do we actually capture it? Well, we have to get clever and force those electrons to take the long way around. And we do that with something called a galvanic cell. You might also hear it called a voltaic cell, but you definitely know it by its everyday name, a battery. This brilliant device physically separates the two half reactions, forcing the electrons to travel through an external wire to get from one side to the other. And that flow of electrons through a wire, that's an electric current. So every battery, every galvanic cell has two electrodes. The anode is where oxidation happens. It's the negative terminal, the place where electrons are released. The cathode is where reduction happens. It's the positive terminal, where those electrons end up. So electrons always flow from the anode to the cathode. A really great way to remember this is red cat. Reduction happens at the cathode. But what actually pushes the electrons to move in the first place? Well, it's a difference in potential energy, kind of like an electrical pressure. We call this driving force the cell potential, or voltage. A great analogy is to think of water flowing downhill. The bigger the height difference, the stronger the flow of water. Same idea here, but with electrons. So how can we predict how much voltage we're going to get? For that, we turn to a table of standard reduction potentials, like this one. Every half reaction has a specific voltage value that tells you how much it wants to gain electrons. The more positive that number is, the stronger the pull, and that makes it a perfect candidate for your cathode. And calculating the cell's total voltage is surprisingly simple. You just use this formula. You take the reduction potential of your cathode and subtract the potential of your anode. And here's the magic part. If the final number, the E-degree cell, is positive, it means the reaction will happen all by itself. It's spontaneous, and it's going to produce electricity. We can even prove this by connecting it to a core concept in chemistry, thermodynamics. This equation here directly links the cell potential, E0 cell, to something called Gibbs free energy, or delta G0. Now, Gibbs free energy is the ultimate decider of whether a reaction will happen spontaneously. So a positive E0 cell automatically means you'll have a negative delta G0, which is the universal sign for a process that releases energy. It's the final proof that your battery is actually going to work. All right, so far, everything we've talked about has been under so-called standard conditions. Perfect lab settings. But let's be real, the real world is almost never that neat and tidy. So what happens when your battery starts to run down, when the concentrations of all the chemicals inside have changed? Does the voltage just stay the same? No way. And of course, there's an equation that helps us figure that out. Meet the Nernst equation. This is our go-to tool for calculating the cell potential under any real-world conditions. What it does is it starts with the standard perfect world voltage, the E0, and then it makes an adjustment based on the current ratio of products to reactants. And that is exactly why your battery's voltage slowly drops as you use it. Okay, now, remember how we said a negative cell potential means a reaction won't happen on its own? Well, sometimes we actually want to force a reaction to go backwards. And we can do that by hooking it up to an external power source. A device that does this is called an electrolytic cell. It consumes energy to drive a non-spontaneous reaction. Think about recharging a battery. That's a perfect example of an electrolytic cell in action. Now, to do any of these more advanced calculations, we need a really special number, the Faraday constant. You should think of this thing as the Rosetta Stone of electrochemistry. It's the one magic number that lets us translate between the language of electricity, that's coulombs of charge, and the language of chemistry, moles of electrons. And having the Faraday constant lets us be incredibly precise. If we know how much electrical current we're using, and for how long, we can calculate the exact mass of a substance that's going to be produced. This is the bedrock of huge industrial processes like electroplating or purifying metals. And that really brings us right back to the beginning. We see this stuff everywhere. From the classic lead-acid battery in your car to the advanced lithium-ion cell powering your laptop. From purifying copper with electrolysis to that slow, unwanted process of rusting. Electrochemistry is all around us. And yeah, speaking of rust, corrosion is really just electrochemistry that we don't want to happen. You can literally think of it as thousands of tiny, spontaneous galvanic cells popping up all over a metal surface, just eating it away. That rusty shipwreck we started with, it's just a giant slow-motion example of this exact process. But the cool thing is, because we understand the science, we know how to fight back. We can put on protective coatings like paint. We can plate a layer of a more resistant metal onto a surface, that's called galvanizing, or we can use this really clever trick called cathodic protection, where we attach a more reactive piece of metal, a sacrificial anode, and let it corrode instead of the thing we're trying to protect. When you think about it, from the very first simple batteries to today's incredible fuel cells and solar panels, our ability to control the flow of electrons has literally built our world. It really makes you wonder, as we get even better at directing this fundamental flow of power, what are we going to solve next?